So, uh,
So let us start.
yeah.
Okay. Good morning, good evening, and good afternoon, dear colleagues. I'm delighted to welcome you all to the International Monthly Seminar Timescales Analysis. My name is Svetlin Georgiev, and it is an absolutely pleasure to see many faces gathered here today. Our aim is to create uh, a meaningful atmosphere where everyone feels included and appreciated. Throughout this seminar, we'll explore many new ideas, valuable insights, and meaningful discussions that matter. Thank you again for being here, and I wish you a productive and inspiring seminar. I would like to ask if Zenir is here or not. Okay, our first lecture for this seminar will be represented by Youssef Rafou, and the lecture is titled Necessary and Sufficient Conditions for Stability via Resolvent and Lyapunov Functionals of Integral Dynamic Equations on Timescales. Please.
Thank you very much. I'm Professor Raful from University of Dayton, and I would like to thank everyone for being here. I would like to thank the organizers for inviting me to be a keynote speaker and the first speaker for this seminar. Today, Georgiev gave the title, and as we shall see, the progress of timescale. I worked those topics I did in the continuous case and the discrete case, and then when I learned timescale, years later, I decided to try it on timescale, but we had to do a lot of work to properly define and prove the existence of the resolvent matrix or the resolvent equation of a Volterra integral dynamic equation on timescale. So once that was done, we had to have the literature developed on Lyapunov function on timescale, and once that done by Peterson, Anderson, and some other people, and myself, and then we had to deal with differentiating the absolute value of x, for example, and so that was once developed, open up a whole area of research. So I don't want to take much of your time. And so I would like to, okay, so this is not doing very well. So we're going to obtain necessary and sufficient condition for the uniform stability of Volterra integral dynamic equation on timescale. And this work will involve two things, the resolvent and separately, and then combined with Lyapunov function, and later on the second part is only Lyapunov function. So, and so if you see, we're gonna, the first part, we're gonna define resolvent, obtain the variation of parameters formula, then obtain necessary and sufficient conditions. Then we're going to do application on comparison to existing literature. And the work of this is done, was work with Murat Adivar and published under this paper. And you can see the result was in 2014. And a lot of this result of this will be in this book by me and Adivar, a book on timescale. It's a monograph of a lot of research papers. So a lot of the recent results are in this book published by Springer. So So let's take a look at this Volterra integral dynamic equation, x delta equal ATX plus T0 to T BTS x of S del S. And this notation here means the intersection of the set with the time scale. And this is our new. Now, we're going to take a look at a function first, matrix function. And then I'm not going to really derive the resolvent, but resolvent is you can find it in the yellow book. And if you need a digital copy, I will be happy to supply you with one. And the resolvent matrix solution RTS of 1 is the unique solution of R delta of S. And this delta here means the partial derivative, okay? Equal minus RT sigma S AS minus sigma of S T RT sigma U BU S del U. Of course, we are all professional here, and I assume everybody is an expert on time scale, or at least the calculus of time scale. So that's why I'm not really doing any introductory work about time scale, okay? So let phi be a given bounded and initial function. We need to introduce the initial function. Then x equal phi t for t naught less or equal to t less or equal to tau naught bigger or equal to t naught. So basically, we're taking a small interval and defining a space of initial function. And xt t naught phi satisfy 1. And this notation to emphasize that the solution depends on tau naught and phi, basically. All right. Again, the next theorem, we derive the solution of 1 in terms of the resolvent. And this basically gives us the new variation of parameters. Let phi be a given bounded and continuous initial function defined on t naught less or equal to t less or t naught. Then xt is a solution of 1 if and only if xt is given by that. And some of you who are not familiar with the resolvent, and you say, well, it seems like the solution is like an integral equation, or in a sense that it involved an abstract term, which is the resolvent RT. Well, that's okay, because later on we will see that we're going to derive condition on the resolvent, and then we're going to use some technique to verify those conditions that will give us the result that we are aiming for, okay? So this is a variation of parameters formula that the solution is in terms of. And remember, this is our equation 1 here, okay? So I go with you for the result, some of the result, in case you may have to do some technique. We're gonna do the product rule differentiation on time scale, and that is 4. Then I integrate 4 from tau naught to t, and then using RTT equal to I, and then inverting, and we will get this equation here, number 6. Okay, now I know what x delta is, and I know what this is, so I'm gonna, or maybe I don't need this, we shall see. So I'm gonna replace x delta because this is my original equation. So xt equal r phi t naught. Now I'm replacing x delta here, plus rt du, plus the last term here. Next, we consider the third term on the right side of 7, 1, 2, 3. So this one, and the order of integration is all justified in the yellow book. So then t naught to t rt, t naught to ub term, double integration, is equal to t naught to tau naught. I'm reversing the order of integration. Sorry, not yet. I'm going from t naught to u. I'm going from t naught to tau naught, then tau naught to u. So I'm decomposing the integral into 2. Then I'm going to change the order of integration, and then I will get something like that. And then if I combine everything, I get this is my variation of parameters. So this inside the integrand better be 0, but it is because RT satisfies this equation. So anyway, so this one is 0 due to 2, and interchange S with U, and we get our proof. All right. So for X in Rn, so we have the Euclidean norm, and this is the norm of a matrix. This is the C, or denote the set of continuous function. And so this is the norm of a function in our space. And this is the norm of, then this is our solution. And such a function is called the solution of 1 through tau naught and phi, and is denoted by xt tau naught phi to emphasize the dependence of the solution on the initial condition and the initial function. So we're going to say the zero solution of 1 is stable if for each epsilon positive and each tau naught bigger or equal to t naught, there exists a delta depend on epsilon and tau naught, such that if the initial function is less than delta, implied the solution is less than epsilon for all t bigger or equal to tau naught. The zero solution of 1 is uniformly stable if delta is independent of tau naught. All right. So the proof of the next theorem is long and tedious and can be found again in the yellow book on page 162. And this is the name of the book, Stability, Periodicity, and Boundedness in Functional Dynamical System on Time Scale, Springer 2020. And is the theorem. Beamer doesn't allow you to label theorem, so I put it part of the statement. So this is theorem 5. The zero solution of 1 is uniformly stable if and only if the supremum for t in the time scale of the norm of all this is finite. It's amazing that that's all you require, finite. Well, of course, we're not talking about asymptotic stability here or uniform asymptotic stability. So all we require is boundedness. And remember, this is the right-hand side of the variation of the parameters formula, if you recall. So again, I'm going to skip it. And then this is couple corollaries that they come out natural of our problem. And then we will have, this is another one. So basically, I'm just playing on the word here. And so forth. So, but I'm going to use this main theorem with my application. All right. So let's come here. In the continuous case, one can easily find that d over dt of the absolute value, the derivative, is x. Let's take a look at the scalar case here, over absolute value times x prime. Now, by using x squared equal this and the product rule on time scale, we can easily obtain this equation here. That is, we call it equation 10. Now, since the product rule is change of this one on time scale, this is the collection. That is the coefficient of x delta in 10 depend not only on the sign of xt but also on the sign of x sigma. Therefore, the equality x delta hold for only if x sigma is bigger or equal to 0 and x is not 0. So let us keep this case distinct from the case x sigma less than 0 by separating the time scales. And then we have a lemma that its proof can be found on page 14 of the book again. And here is the lemma. Let x be not 0 be differentiable. Then x over x, absolute value of x delta is equal x of delta for t and the t plus of the time scale. And then it satisfies its pinch between these two upper bound and lower bound for t in the negative time scale, or whatever you want to call it. Negative, it's not listed, but I call it t minus. So this is bigger or equal to that, less or equal to minus that. Okay, now we apply, so we're going to apply the result of theorem 5 and prove necessary and sufficient condition for the uniform stability of And now I'm looking at the scalar equation. And this is AT equal XT, X delta equal AT XT, T naught to T, BTS, X of S del S. So let's think of it, AT, BTS. So really, if you look at this equation, AT either changes sign or doesn't change sign. So really you have the magnitude or the integrability of BTS, mean the size of it. So this is only thing you have to play with. So let's see how this plays out. Suppose that AT does not change sign, so either positive or negative, then the zero solution of 12 is uniformly stable if and only if there exists, I think I need an S here, there exists a constant K such that AT plus K T naught to sigma of T BTS del S less or equal to 0, and the minimum of AS minus plus 1 over K, AS 1 plus over K is positive. So let's take a look at this condition for a second. If AT is negative, K can be positive or negative, but then it depends on here what we need out of it. Because if A is negative and K is negative, so that is positive, that is gonna be depend how big K is, you know what I mean? So this is kind of tricky, but if A, but we're saying A doesn't change sign, so if A is positive, K better be negative. You know what I mean? If A is all positive, then K better be negative. Okay. So let's see how we do that. Okay. We make use of the previous lemma in VS. So I'm going to define a function. Actually, it turned out to be a Lyapunov function. RTS plus S to T, T naught to S, RT sigma U, BUV del V del U. Now we know how to differentiate this with respect to S. Minus, we could use the Leibniz rule, and all these stuff are proven as a part of the calculus of timescale. So we get minus 0 sigma S RT sigma of S BSV del V plus S to T RT sigma U BU. And this comes from the differentiation of that. So this is bigger or equal to this RTS to that minus 0 to sigma and plus this term here. Okay, so this is or equal to minus, now I need to put the delta TS here by its value. And this is going to be bigger or equal to sigma TS minus A minus all that. And now, so this is all that bigger or equal to minus RTS, all this minus blah, 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 where we have used this one is bigger or equal to that one. Now, if RT sigma of S bigger or equal to 0, then this one can be written like this. And as a consequence, we have from 15 that V delta bigger or equal to minus AS minus that. And if you use the condition 13, you will get this one. So now, if RTS or sigma is less or equal to 0, then RT sigma is minus, and as a consequence, we have from 15, this is equal to AS minus, and then BUS del V RTS, and this is bigger or equal to AS plus all that. Okay, where we have U13 again. Thus, combining 16 and 17, we have V delta S bigger or equal to gamma S RT sigma, where gamma is the minimum of these two values, this one and the other one. Okay, So what does that mean? So the derivative is bigger or equal to 0. That means V is increasing, not decreasing. So this, along with 14, yield that for any tau naught with T bigger or equal to tau naught, we have V tau naught less or equal to VT. But look at VT. VT is RTT, and RTT is 1. So V of tau naught less or equal to VT, RTT equal 1. Thus, A is satisfied since RT tau naught, because V tau naught replace S with tau naught, you will get this one here, and that is a condition for the if and only if. Thus, 8 is satisfied with RT tau naught plus all that equal V tau naught at T, which is less than 1. Okay, so we have our result. Okay, so let me take a time scale, which is a discrete, positive discrete, or non-negative. I'm going to take T equals 0, 1, 2, and so forth, and kind of consider the scalar equation. Xt plus 1 equal xt over 2 minus s equals 0 to t xs, s plus 1, s plus 2, which can be expressed in the form of 12 as follow, because 12, the x delta, the analog of it in the discrete case is del x, which is xt plus 1 minus xt. So we need to write this in this form. So we have, so here at now is minus, because you're going to add minus xt here, minus xt here. So you'll get del xt equal to this one by definition. Then at is automatically minus 1/2 minus, because usually in discrete we need a t minus 1. So I will have at t minus 1. So this becomes xt, which is a part of at, and bts is 1 over s plus 1, s plus 2. All right. So if we let k equal minus 1/2, then we have at plus k, all that equal minus 1 over t plus 1, t plus 2 plus 1 over 2 times t plus 1. And that is less than 0. And so for t between in the discrete, non-negative discrete, the minimum at minus 1 plus 1 over k, at 1 plus 1 over k is 1/2 plus. That is positive. This means condition 13 and 14 hold, and the zero solution of 18 is uniformly stable by theorem 5. Okay, so in example 3.1 of the paper, Tauheed, he was our graduate student, and that was in year 2002. So that's how back I have gone. So this was published in Journal of Difference Equation and Application in honor of Professor Alan Peterson on the occasion of his 60th birthday. So me and Tauheed did ask for the existence of k between 0 and 1 such that minus at plus k minus s equals 0 positive. All right, so in order to show that vs plus 1 minus vs is positive, which is needed for the uniform stability, we're gonna rewrite the problem. Then we have at equal 1/2 bts, and then minus at plus k minus equal minus 1/2 plus k over t plus 2 is less than 0 whenever k is between 0 and 1. Hence, condition 19 does not hold here. So this is compared to our example when I took in this case here. Okay. So here is an example where the time scales, because I defined the way we did the proof, and the time scale basically corrected the proof of the continuous case, and that's why we were able to do that. And now another comparison in example 3.1 of the paper Elo, Islam, and Bozang, and that was in Dynamical System and Application in 2000. the authors considered the scalar equation ATXT plus 0 to T BTS XS ds and the Lyapunov functional, this Lyapunov function. Okay, in order to have this, they assume the existence of a constant K bigger than 1, such that for T bigger or equal to 0, AT plus K 0T less or equal to 0. So our K was able to change depend on the sign of A. You see the difference? So the above condition is needed to show uniform stability. We observe that our conditions 13 and 14 allow K to be negative. For example, if we assume A less than 0 and take K equal minus 1/2, then we have the minimum of these two values is minus A as positive. Therefore, condition 13 is satisfied for any function BTS. So that is another improvement. Now, this is the second part of the proof, the second part of the talk. Here, we're going to rely on Lyapunov function only. Okay, so AT is continuous, CT is continuous, and T and right dash continuous with respect to the second variable. S belong to this intersection with the time scale. So we establish necessary and sufficient condition for the stability of the zero solution of scalar 21, of the scalar 21 Volterra. Okay, this is, I need to straighten my English here a little bit. On general time scale, our approach is based on the construction of suitable Lyapunov functionals. All right, so suppose CTS is right dash continuous. Let this one del U be continuous for T in the time scale. Suppose A is a continuous function on this, and there are constant nu bigger than 1 and alpha comma beta bigger than 0, such that 1 is plus mu AT in absolute value, 0 to T CTS del S plus mu T A squared plus nu sigma T infinity minus 2AT less or equal to minus alpha, and mu T times this term here, minus gamma minus 1, minus gamma minus quantity nu minus 1, and less or equal to minus beta. Then the zero solution of 21 is stable if and only if AT less than 0 for all T. So here only we're requiring AT to be less than 0. And we are requesting these conditions. All right. So here is the proof. We're going to take VTX to be x squared plus nu 0 to TT sigma u del u x squared of S del S. So we're going to assume AT is less than 0. We have along the solutions of 21 that. So here we are applying the product rule. This will be 2 mu. It's like, this is like, the first term is like what we have in the continuous case, is 2x x prime plus mu times the right-hand side of x prime square. So that will be this one. So if mu equals 0, of course, we get the continuous case here. There's nothing to worry about, right? Minus nu 0 to T CTS x squared of S del S plus nu sigma of T infinity CUT x squared of T del U. Okay? So now we really need to write these out, express this one, and combine with these last two terms and try to simplify and see if we can get our conditions. So now I am talking about V dot, which means the derivative on time scale of V with respect to T. So that is minus 2a x squared. So basically here, okay, because a is negative, so I took the absolute value of it. That's why. So in mind, I'll be comfortable that this is always negative, so I don't mess up. And in case I forgot a is less than 0, plus 2x, that is this time of that, plus mu and I'm expecting this square of the second term, and then minus the last two terms. So we're gonna use this fact. This is one of the simplest inequality ever to exist, and it's so powerful in reducing Lyapunov, the derivative of Lyapunov functional. And this comes, the proof of this is, you notice A minus B quantity square is bigger or equal to 0, and then you get this one. It's as simple as that. So 2, 0 to t, that one. So let's apply A, B to this. So that will be x squared plus x squared, because we divide by 2 and we have to. Also, using theorem, yellow book, page 16, this is the some kind of inequalities. I forgot what the name of it. And 0 to t ct as xx quantity square, I'm going to write this to the power 1 half, and x, I'm going to write it like this. And then this is less or equal to 2. This one is squared, which is this, plus this one is squared, which is this one. Now, if I put everything together, I will get less or equal to minus alpha x squared of t. We already know that. And so we have two things going on here at the same time. Okay, now let epsilon be a positive, be given. We will find a delta positive, so that for any bounded initial function, phi from this interval with the norm of phi less than delta, we have x t naught phi less than epsilon. Due to 26, v is decreasing here, unlike the other theorem. And hence, for t in that, we have that x squared less or equal to vtx. Why is that? Notice here, x squared, v is the sum of two positive number, or two positive quantity. So that means x squared is less or equal to v. So that's what I'm using here. And since v is decreasing, that is less or equal to vt naught phi. And vt naught phi, I'm going to replace x with phi with the initial condition, you see, because it's t naught, 0 to t naught. I am looking at t naught. So this function becomes, this x that was before is from, it's integrated over the initial interval for the initial function. So they become the initial function. I factor it out, then I'll get 1 plus nu 0 to t naught to phi cus del u del s, and this one, or xt t naught phi less or equal to epsilon. For this proves uniform stability. I just want to mention something here about the Lyapunov function. If if I took x squared here, not absolute value of x, because I have x squared here. So when I evaluate vt naught, I need to be able to pull the same quantity out, not phi and then not phi squared. You see? Now, you guys can try, if you take the absolute value of x here, and you take the absolute value of x here, and see if you can get any meaningful different result from what I did. I did not try it, but I'm sure if you use the absolute value of x, since now we know how to differentiate it, you may get something out of it. Okay? So now to prove the other part, we assume AT positive. So now what we showed is if AT is always less than 0, then we have uniform stability. So now we're going to assume that if the 0 solution is uniformly stable, then AT is always less than 0. So we're going to do it by contradiction. So we assume AT is not a positive for all t. We assume AT is positive for all t. So then this define the functional Wt equal x squared minus mu x squared. This is not a Lyapunov function because it could be negative. And then along the solution, if you do certain calculation, you can show that the W is here bigger or equal to 2a minus 1 plus mu a minus mu a squared minus that plus this one becomes, okay, so this is bigger or equal to alpha x squared. Okay, because this is positive, it becomes a positive. Okay, and then this becomes the negative alpha, so this is bigger or equal to alpha x squared, which is pretty good. Then I do some work here and I show that x squared bigger or equal to tw bigger or equal to that plus alpha that, which is goes to infinity. As t goes to infinity, x goes to infinity, which is a contradiction to the fact that the zero solution is uniformly stable. So that proves the other part. Now, when t is r, condition 23 becomes unnecessary if we take nu equal 1, and condition 22 reduces to 0 to t plus t to infinity cut minus 2at less or equal to minus alpha, if t equals to r. So you see the time scale, you really have to work harder to get where you want to get. And it seems like any time now I want to do some work on time scale, I'll try to do it on the continuous case first and see what I get. Then I turn around and I extend it to the time scale. And then that gives me more confidence. And then I know how things work on a discrete system. And then I can compare the both. All right, here's some corollaries. We're going to assume a 22 and 23 hold with at less than 0, and at is bounded for all t. Then x squared is bounded. X squared is an L2. Okay? And x delta, the derivative, is bounded. And the zero solution of 21 is asymptotically stable. But I do not have a necessary and sufficient condition here anymore. So all right, here's another theorem. Consider 21. Let's see what is, 21 is our equation with at less or equal to 0 for ALT. For all t in 0, infinity, we assume the norm of A minus that is bigger or equal to 0, then the zero solution of 21 is stable. Moreover, if there exists a T2 bigger than 0 and an alpha positive with bigger or equal to alpha for S in T2 to infinity, and if both Ct and At are bounded, then x equals 0 is asymptotically stable. Again, I do skip this proof. It follows from the other work. I deviate my Lyapunov function a little bit, and I do get that this theorem. Okay, so now let us take t, let us do application to q difference equations. Let's take t equal to qn, q to the natural number, which is q to the power n, n in n, and q bigger than 1. On this time scale, 21 takes the form dqx equal atxt plus s is in 1t intersect with the qn. This is the mu ctsxs, and t is bigger or equal to 1. And here 1t qn is 1t intersect with the qn, and the grayness is q minus 1 times s. And the derivative on the q difference on the q difference time scale, the derivative is given for any function phi is phi qt minus phi t over the grayness. Okay, or mu qt t in qn. All right, and c is in this time scale is continuous function and A goes from here to R is also continuous. And we're going to let AT equal minus Q over T cube minus T plus 1 over T, comma CTS equal 1 over T square S square for TS in this, and let T equal Qn. And since this bigger or equal to minus 1, we have that 1 to T, this is bigger or equal to that. 1 to T CUS del U is 1 over S square, 1 to Qn, that is 1 over S square, Q to the power 0, Q, integral plus integral Q to Q square, plus Q square to Q plus Qn minus 1 to Qn, and over 1 over T dQu. And this is the sum of all these. When we have 1 over S square out, K equals 0 to N minus 1, Q to power K, sigma Q to power K, 1 over U square dQ U. And so this integral, we know on time scale, is mu Q to the K, 1 over Q to the power 2K. And that is 1 over S square, K equals 0, N minus 1. Q minus 1 QK, 1 over Q to the power 2K, and that is 1 over S square, Q minus 1, K equals 0 to 1, 1 over QK, and that gives us 1 over S square Q. Beautiful. Thus, AS minus sigma S of that is bigger or equal to 1 over SQ plus this is from A, minus 1 over SQ. You get S plus 1 over S, that is bigger or equal to 1. Thus, all the conditions of the previous theorem are satisfied with T2 equal 1 based on the definition of stability we considered, which implied that the zero solution of 29 is asymptotically stable. So I thought that was very interesting result, that it's not only discrete, continuous, you got a Q difference equation, but you really need to know how to manipulate the algebra of it, of the Q difference equation, the calculation. And and this is the theorem Adivora mentioned before. This is theorem 5.2. Suppose that AT does not change sign, then the zero solution of 21 is uniformly stable if and only if there exists a constant K such that less or equal to 0. This is positive. All right. Now suppose AT less than 0 for oil T. Then from our condition 28, we have K equal 1. Thus, as a consequence, condition 31 cannot hold this one. I'm just reminding you of what we proved before. Since the minimum of if this one is equal to 0. And we know that this minimum has to be positive. This is the first part of my today's talk. So with the second part of my talk, I improved the first part of my talk. All right. In example 2.3 of the previously mentioned paper by Elo, Islam, Deng, when T equal R, the real, the authors considered 21 and assumed the existence of a constant K positive, such that for T bigger or equal to 0, AT plus K 0 to T CT as less or equal to 0, then the above condition is needed to show uniform stability. Condition 32 imposes size limitation on CTS. Precisely, we must have less or equal to minus 1 over K AT, or 1 over K AT for K bigger than 1. On the other hand, our condition 28 does not require, is less restrictive and only require less or equal to AT. All right, so I'm really, I will leave some time for questioning, but so what did we do? So we took, and this work, as I said, was published in 2014. most of it 2014, 2016, something like that. And I compared it to papers that were written in 2000 and 2002. So that shows the importance and the validity of the of doing work on timescale, because I was able to go back 14 years later, 14 years ago, and not later, 14 years back, and pull up some result and show that the timescale did really improve on them. So I thought that was amazing, and that's why the both papers both work were published in good papers. And here I just want to have open problems. In the spirit of this talk, what can be said about the asymptotic stability of the zero solution of the scale? Typo. Asymptotic stability, yes, of the zero solution of the scalar Volterra integral dynamic equation x delta equal ATX plus 0 to T CTS XS del S. And what I mean by asymptotic stability, I mean regular asymptotic stability means the solution is stable and the limb of xt goes to 0, st goes to infinity. And then I'm talking about the uniform asymptotic stability. Is it possible to extend the if and only if for the uniform stability to the uniform asymptotic stability? That will be an amazing work if it can be done. Plus, I don't know if maybe you have a graduate student or something can do examples, do some examples related to vectors, because in the example I use the scalar, as you noticed. So it will be interesting to write similar equation, do similar examples on vector integral dynamic equations. And references beside the papers and other work, at least reference for this talk, is our yellow book, Stability Periodicity, blah, on timescale in Springer 2020. And thank you. And if there's any questions.
Thank you very much for your interesting lecture.
Thank you.
I would like to invite all participants for questions and remarks.
Hello, sir.
Yes.
Am I audible? Am I audible to everyone?
Mm-hmm. Yes,
Am
yes,
I
please.
audible? Okay. Basically, it is a great presentation and nice question.
Thank
Firstly,
you.
my question is, you have considered the equation x delta of t equals to a of t x of t plus some non-homogeneous part. And by explaining the solution, you have considered that a of t and non-homogeneous part should be continuous. It
Right.
means RD continuous. So can we say also that if our equation in such a form where a of t and non-homogeneous term are not RD continuous, can we find a solution in terms of resolvent, or we can say in evolution operator?
Yeah, the resolvent only exists for when all the terms are continuous, unfortunately.
Okay, it means is there any result on
No.
such kind of equation where these are not?
Yeah, there are resolved, but not not using resolvent. Yeah, there are
Okay,
a
not
lot of
using
resolved,
the.
but not using the resolvent method.
So what they have been using for this kind of,
I really
it would
don't
be
know.
great for me.
Usually people use, I don't know, anybody can step in and help me out if they have experience with this. If the kernel is not continuous,
Hmm.
so I think people are using degree theory, the people are using fixed point theorem to show the existence of solution, but I don't
Okay,
know
okay,
if it's related to stability or not.
okay,
People are using fixed point theorem to show the existence of solution, multiple solution, and so forth. But what I can suggest is the following. If you go
okay.
here, and
Yes.
if I mean the resolvent equation exists for the linear case inside the integral. If you don't have a linear term in terms of x, then the resolvent will not work because it's a linear operator. Okay? The way it works. So what you can add here, you can add x of s plus some function, gsx of s. And so you have xs plus a g as a nonlinear function of s, x of s times cs, cts. And then what you should do is you will write, you know the resolvent for the linear part. So split the equation into two equations and then use the variation of parameters formula to obtain a new variation of parameters formula. Like for example, you have, if people have like atxt plus 0 to t this, plus some function g of t here. And then they can combine this function with the variation of parameters. So what I'm saying is you can add nonlinear function here and do some work with the resolvent. And recently I published paper in the Journal of Timescales, is that right, Georgiev? That address part of this, what I'm saying, address part of it. So, but for the non-continuity, I've rarely seen anything that uses either Lyapunov function or the resolvent.
Okay.
Anderson, do you have any idea? You are muted.
No.
My only idea is if the time scale is completely isolated, but with a varying graininess, there are still some interesting questions, and it would automatically be continuous because it's an isolated time scale.
Yeah.
But it would include the discrete case, it would include the Q difference equations case, it would include some other interesting cases, and then that way you wouldn't have to worry about continuity. But I don't know. I don't know. Then I mean, your results would still cover that, wouldn't they? Because everything's automatically continuous in that case.
Yeah. So
But
yeah, and there is a book. Let me show you. There is a book by Ted Burton. This one. And I think you can download the PDF online for free. And then he uses, but this is for integral equation. And sometimes he differentiates the integral equation to obtain a Volterra integral differential equation. And he does have some kernels that I'm not sure if they're not continuous though, but because he always required the kernel to be bounded, to be integral, for the integral to exist of the kernel. So, other questions?
Yes, there is one other question.
Sure.
Actually, I have also faced the difficulty to solve these kind of equations. So firstly, it was quite difficult for me to find the resolvent operator on time scale for the particular example. Let's say we have considered a of t in any such form like sine t, anything we can take. So for that type of equation, I am not able to find resolvent operator on time scale. It was quite difficult for me. So can you discuss some example where we can find resolvent operator on time scale for such type of problems?
Okay, what I would really suggest is you go backward. First of all, as you notice in this talk, I never bothered to find the resolvent. We just obtained conditions on it, and we verified those conditions through Lyapunov functionals. So we did not have to do it. But for my recommendation, go ahead and start with a continuous case. Let's say you take x prime equal atx plus 0t cts x of s ds. Multiply both sides by the exponential of e to the T naught to T, AT, DT, whatever, multiply by the integrating factor on both sides, and you obtain an integral equation. And then you know what the resolvent looks like. So compare your variation of parameters formula, the one you got by multiplying by the integrating factor, compare it with the exact solution in terms of the resolvent, and you can eyeball the resolvent. You see what I mean?
Yes, yes, sir.
So solve this one without the resolvent, multiply by the integrating factor, solve it, and then write down the resolvent and compare both. And
Okay,
you
sir.
should be able to eyeball the resolvent.
Okay. That will be great. Thank you,
Yeah.
sir. Thank you, sir.
Mhm. So if anybody wants a copy of this book, digital copy, I will be happy to send you one. And it has a lot of recent topics on timescale, a lot of Lyapunov functionals, a lot of this material related to my talk today, and a lot of examples that I work in detail on timescale. Other questions?
Yes, sir.
Yeah.
I have a question.
Yeah.
It is related to Lyapunov functional.
Right.
My question is how to identify how to choose Lyapunov functional for stability.
Okay. Well, you see, for this
Because
one
that
here,
is a long question for me.
Yeah.
That is a long-standing question for me. That is how to identify a particular Lyapunov functional
okay.
to
All right.
study the stability.
Okay. For example, let's take this one here, this equation. Let's take this. Let's assume this is 0. This 0 to T CTS XS does not exist. So if you want to find the Lyapunov functional for that, you take the absolute value of x or x squared for this term only, right?
Yeah.
Yes. But now you have an integral. So you need to do a term for this integral. So that term has to exist and plus another integral, because you see, if you only consider absolute value of x or x squared for this, and what do you get? You differentiate, you get 2x x prime. So you get 2x times a squared. You get 2x squared a, correct? You get 2x squared a if a is negative. But then how do you solidify this term? So you need another term in your Lyapunov functions that has double integral. So when you use Leibniz rule, you integrate from the bottom, you get negative term. So you need as many negative terms as you can. And Leibniz rule will give you the negative term. For example, like here.
Yeah, sure.
Like here. So this will be for the linear term only. If I have x delta equal ax, that will do. But since I have the integral, so you see 0 to t, this term exists already here. And then I add this one, t to infinity, and the del u, cus del u, x squared of x, I don't touch, it's from 0 to t here. And you see, I integrate Leibniz rule. When you do the integration of this, will give you negative term. And the negative term with the positive integrand. So you have now, and then because when you put your solution in, you have a positive integral, and then the negative term you get from here will negate it. Because you want the derivative of the Lyapunov function to be less than 0. You want it to be negative. That's the bad thing to do. So you need to create terms that give you negative term. And that integral will give you one negative term. You look at it, there it is. That integral gave us this negative term here. And then when I put the integral in its place, it concentrated with some of the other ones here. So I was able to compare this with that one after I did some work on this. Yeah. So that's how you do. I mean, it's if you have a Volterra integral equation, you just need a term in the Lyapunov function of double integral. Yeah.
Yeah.
Other
The
questions?
integral term should be there. Yeah.
Yeah. If it's not there, you're not going to get anything to cancel out some other positive term, and you have no control over them because there will be x squared s under the integral. So you cannot do anything with it. You want it canceled or less or equal to 0 with some other term. So you can get rid of it.
Yeah. Okay. Thank you.
Mm-hmm. Other questions? So do we have one next week, right? Georgiev?
Yes, your examples are in the cases when the time scale contains
I can barely hear you. You're cutting out.
Is it possible to give?
Is it possible to give examples other than continuous, discrete, and Q difference?
Yes, yes.
Yes, it is. It is very possible. But you remember, you need your grayness to be bounded. You know what I mean?
Yes. But there are time scales in the form take U to be 1 over 2 power k sequence.
Yeah.
And then consider the time scale 1 minus U union with 1 plus U.
Right.
The 1 is Rydens point.
Yeah.
Is there possibility to prepare example for such cases?
Yes, it is. As long as this mu here is bounded. Yeah. And you can do any. Yeah. As long as this mu is bounded. Why? Because you see here, look at this mu here. We want it to be less or equal to minus alpha. Because this is a positive term.
Yes.
So we need a mu to be bounded. And so that's why any time scale with a mu being bounded, it's a fair game to give an example. And I really, as someone who's accepting time scale and I've done a lot of work on it, I am more open to papers where people just do some hard examples to already existing theory. You know what I mean? Because the examples in timescale are rare. I get so many papers to referee, and there's no meaningful examples at all. And I have to reject because you do work on timescale, and then you don't give any examples that are outside, as you said, Georgiev, the real or the discrete, and then I'm sorry. We should be able to do better. Yeah, we should be able to do better.
So, thank you.
Again, email me if you need a digital copy, really. I mean, there's a lot of open problems in this book. Each chapter has 2 or 3 open problems in it. And a lot of them are still open. And I'm not making any money off this book, 0 money I'm making. So I will be very, very happy to share my digital copy with you or from the publisher.
The book is very good. And
yeah, I shared it with you, right?
Yes, yes.
Yeah.
And we have solved one open problem here.
Yeah. I mean, it's it's my co-author, Murad Adivar, is really, really good mathematician, and he learned this area. We learned it together. He was in optimization, and then we were able to write together about 18 papers, and then we decided to write a monograph. And but he's in economics. He doesn't do any math anymore. No math department will hire him. So economic department hired him, and he's making tons of money. So, so at least it worked out for him. So,
Other questions? The book is excellent.
thank you.
Yes.
I really appreciate it. I'm glad you like it.
Mhm.
Yeah. Yeah, as you could see, there's a lot of examples and open problems, but people are willing to work. You have to
Yes.
put a lot of work into the calculus of it. Yeah. So Douglas caught up with time scale before I did. I came late. I was not a believer at the beginning. Then later on, I had a more open-minded. I am like a Ted Burton student type of researcher. And then I moved on. I decided if I'm gonna survive, I need to learn a new stuff. So
Next
Yeah,
question.
and in the first chapter, you have given the derivative of mod x, modulus of x, absolute
huh?
value of x.
I
That
I
I can
can.
find, yeah, in the first chapter of your book, that is yellow book, this one.
Yeah. Oh wow. Okay. Yeah.
You have given the derivative of absolute value of x. That I
Right.
find only in this book, not any other book.
No, you can't find it. This was published by paper by itself. Yeah.
Yeah,
And once we did
but that
it,
proof is very nicely given it is.
yeah, and once we did it, it opened up the gate for a lot of research.
Yeah. And
Yeah.
in every chapter, at the last, you have given several open problems.
Yeah.
So that is interesting one.
Thank you very much. I appreciate the compliment.
And even the recently your difference equation book.
Oh, do you like it?
Yeah, I referred this book for teaching. So this semester I introduced the new course, difference equation.
Uh-huh.
And I am referring your book and Kelly Peterson's book.
Okay, good.
So your book is very interesting and some interesting examples are given at the exercise.
Good.
Yeah. So language, the flow is very simple. Language is also very simple. So
Yeah.
our undergraduate students, they also
Yeah.
liked very much.
Yeah. Well, I mean, as you see, I had 4 kids. They're all gone. My wife is almost traveling to see my grandkids out of town. So I decided I'm gonna write some books in the meantime. So, and I found the publishers were very open to my ideas. So that really helped a lot. Because if I was receiving negative feedback, I would not have attempted it so many times. But the feedback was almost positive. And once I got away from certain people, you know what I mean? You always have this 1 or 2 person in your life, in your professional life, that kind like want to set you back. But once you get away from them, things will go fine.
Yes,
And
I agree.
I met Georgiev about a year and a half ago, and we have a great working relationship. And I really appreciate his feedback and all his experiences that I learned from him.
Yes, I believe that in the further to solve some of the other open problems in your book.
Okay, good.
Yes.
Yeah, good.
Yeah.
But the
We
techniques
can work on
the techniques which we propose is the fixed point theorem.
Right.
Yes.
Yeah, thank you. Okay.
Next questions, comments.
If after your permission, Professor Svitlin.
Yes, please come.
Yes, I would like to thank Professor Yusuf for his great works, for kind presentation, and also many thanks go to honorable assistant. In this occasion, I am pleased to invite to submit. We prepared the second issue of our journal. If possible, we need to submit some paper related to timescale, of course, analysis, and thank you in advance. I hope we will see you in the next conference, and thank you.
Where is the conference?
In the next monthly conference.
Okay, here. Yeah. Okay. Yes, you're talking about the Journal of Timescale Analysis. Is that right?
Yes.
Okay.
If possible, some papers related with this subject in order to to publish the second issue.
I think I did put a paper there with two of my students. They are PhDs now.
Thank you so much.
Yeah. Thank you. I appreciate it. We need the dog's help.
Of course, it is for us.
Yeah.
For all.
Yeah. Yeah, I think your journal is the first journal on timescale, isn't it?
Yes.
Yes.
Very good. Excellent. It's about time. I was gonna do one, but my institution is too cheap. They would not support me at all. So I said, heck with you. So
Great.
I'm glad you guys did one. And I don't know how I came across it, but I came across it by mistake, I think. And then once I found the George, and that's like, all right, that's interesting. Yeah.
Oh, yes.
Yeah, I was looking for something and it came up. Then I looked it up and I looked at the editorial board and everything. So I did like it.
Thank you. Thank you.
I'm sure it's gonna be a great journal.
We believe.
Any other questions?
Yes. Comments, questions? If not, I would like to thank you again
Just
to
a minute, Professor Zvidlin. I will share the link in the chat.
Okay.
Okay. I would like, yes.
Just a minute. Okay, this one. Okay. Thank you for all.
Thank you. Thank you very much, guys.
Thank you. See you.
All right. Can we stop now?
Okay. I would like to thank you again to Youssef Rafou for this very interesting keynote lecture. I would like to thank you to all participants for the fruitful discussion on the topic integral dynamic equations on timescales. Really, all books by Youssef Rafou are very good. I very like, and I recommend to all of you to use his books. So I would like to remember that the next seminar will be on 25th October.
Okay.
Then we will have two talks. The first talk will be by Sanket Tikare, Wirtinger type dynamic inequalities. And the second talk will be by Said Ben Sliman, that is connected with Toeplitz matrices and timescales analysis. This will be on 25th October at the same time, and all of you are welcome.
Thank you.
Thank you again.
Yeah, thank you for having me. It was really an honor and pleasure to be here with you guys.
For us too.
Okay.
Thank you.
And let me know if I can be of any help to you in anything, okay? If you're working on any of the open problem, if you want my advice, any opinion, please let me know. Okay?
Yes.
And look my books over Amazon or eBay or the publisher. And if you need any digital copies, let me know. Don't buy them. I'll give you digital copies. Okay. My latest one, I don't have the digital copy for the Fourier series. I don't have a digital copy yet, but in case I get one. All right. Thank you very, very much, guys.
Thank you.
Thank you.
Thank you.
Bye.
Thank you.
See you next
So,
month.
Professor,
Yeah. See you.
Yes.